of this chapter very soon. Right, so this is from chapter 4, 7, and 8 of this book. So let's start with Schrodinger equation. You know Newton's law, right? F equal to ma, reaction equal to action, and then Newton's first law. These are the governing equation. You use the equation to determine how the system will evolve. Then what is Schrodinger equation? It's just the governing equation for quantum mechanics. Okay, so let's take this for granted. So in principle, you cannot prove Schrodinger equation. Okay, but you can check its validity. So up to now, more than 100 years, it still works, right? As far as I know. Of course, there are some questions in some aspects, but most of them are still work. We are using our transistor based on Schrodinger equation because all the band diagram are derived from Schrodinger equation, right? So let's look at it. What is Schrodinger equation? First of all, as I said, this is the governing equation for quantum mechanics. So what we want to know is that for a system, right? For every system, it has, my spelling has some problem today. For every system, it has a state. And now I directly write it as psi, which is ket. You know this is a vector. This vector can be very large, right? In a very large dimension, just like to describe the state of this classroom, we only need one vector because we only have one state at that particular moment, right? And it must be evolves, it will change. Evolving under a Hamiltonian. So we did not really discuss what is Hamiltonian, but basically, we just take it for granted. Hamiltonian is just the total energy. Now, this total energy, of course, is not as simple as just like how much energy it has. It has a landscape. You talk about how the energy change as a function of location. It is a function of time, etc. And this is easy to understand. For example, if I just say that, okay, I have a roller coaster and it has this landscape. This represents the energy of this system at different location. And then I have the cart maybe here. And it may have an initial velocity v. If I am given this energy landscape, of course I can predict how the cart will move, right, as a function of time. When it's going to accelerate, what's the velocity, what is its position. So it's not difficult to understand that in principle, if I have the Hamiltonian of the system, which can be very complicated, even in this case you see that it is a function of location, I will be able to know how the state will change, how the cart will move, right? So if you go back to this more abstract space, we say that I have a state which has a state psi. It will evolve. Evolve means it will change as under the Hamiltonian as a function of time, right? So let me just emphasize again, this Hamiltonian, you can think it as the total energy of the system, right? You can write it as h of x. Here I put it vector because it is 3 dimension, right? So x, y, z in mean, right? So what is Schrodinger equation? Schrodinger equation, SE, right? This is S dot E dot, right? Basically, it is this. It say I, H bar, partial, psi partial t equals to h psi. Simple. Also can be scary, but it is not. Because just remember, what is the meaning of cat psi again? It's a vector. It's the state of the system. So what it tells us is that the rate of change of the vector, partial psi partial t, means that how fast it changes, is proportional to the Hamiltonian multiply that vector. So it is very simple actually, just like F equal to ma, right? Of course, this is not F equal to ma. And it also scaled by this I, which is imaginary number, and h bar, the reduced Planck constant, right? So that's it. Any question about this? So it can be so simple, and we really don't need to spend time to appreciate at this moment, right? But the good thing about this class is it is about quantum computing, and we are only talking about 1 qubit or 2 qubit. For 1 qubit system, let's just think about 1 qubit. What is the general form of psi, by the way? Anyone can tell me? Let's say you need to teach quantum computing. Yeah. We have, yeah, mention.
0 plus sine theta over 2 pi.
Very good. So he actually gave the representation on broad sphere. But I'm not asking for that. Can we step back a little bit even earlier before we introduce broad sphere? What do we say? You are right already. Thank you. Alpha 0 plus beta 1, right? Basically, you only have 2 parameters. And how do you write it in the column form? Alpha, beta, right? That's all we have. So if I plug in this equation, plug in this side into here, this becomes a 2 by 2, this is a system of 2 linear equations. Then what will be the matrix? What will it be? The form. It will be 2 by 2 also, to make it reasonable, right? Maybe you don't see it yet, but let me just write it down and you will see why. Why this is correct. Then this means that the H, the Hamiltonian, must be 2 by 2, so I'm going to write it as H00, H01, H10, H11. Right? So this is that I write it in the matrix form of the Hamiltonian. Now, if I plug this into the equation, what I get is I, H bar, partial, I just put everything, alpha, beta, partial t, equals to H times alpha, beta. Or actually, H is H00, H01, H10, H11 times alpha, beta. This is a little bit confusing, this one. But what it means is basically this. I, H bar, partial alpha, partial t, partial beta, partial t. Or I can even put it as I, H bar, partial alpha, partial t, I, H bar, partial beta, partial t. Because I'm talking about a vector. It has 2 elements. When I say I do the differentiation against with respect to time, it means that I do it for each element. So that's why it's partial alpha, partial t, partial beta, partial t. And then, of course, this constant can go in, right? Again, a constant times a vector, it's just every element will get multiplied by that constant. With this, how can I make the left-hand side equals to the right-hand side? It means every element must the same, right? In left-hand side and right-hand side. So basically, it says that I have 2 equations. I h bar partial alpha partial t equals to H00 alpha plus H01 beta. Second equation is I h bar partial alpha partial beta partial t equal to H10 alpha plus H11 beta. Give me a system of differential equation, right? Never just call it DE. Or linear equation. Okay. Any question up to here? Now, I know there's a lot of math, but if you do it step by step and accept some of the given conditions, they are not difficult. Again, you take it for granted. That's why he's so famous, called Schroedinger equation. So even you don't know how you get this, fine, just accept it. This is the Newton's law for quantum mechanics. It says that the rates of change of the states proportional to the Hamiltonian times the state. Done. How do we use it? Here I'm trying to write it in a matrix form. Some of you has worked on the wave equation. They are equivalent. What you do is just project this into the real space, right? We're not going to talk about this, but this is just a projection. When you project a state into the real space, then you get the real space wave function, right? But we can discuss more if you're interested in understanding this. Now we just take it for granted. You can make it in a matrix form. So for 1 qubit, it is a two-dimensional system, alpha, beta. Just plug in. Then the corresponding Hamiltonian must be 2 by 2. And you just equate them. Then you get these two equations. Basically, it's saying that the rate of change of alpha, because the state is defined by alpha 0 plus beta 1. If I know alpha, I know beta, then it means that I know how the state evolves as a function of time, right? I just need to know alpha and beta value at every time. Then I know what the state is. That fulfill the purpose of understanding how the state evolves, right? So here is that the rate of change of alpha is equal to H00 times alpha plus H0 times beta. The rate of change of beta is equal to H10 alpha plus H11 beta. Right? You don't need to memorize. I just want to tell you that what we see from here. But I hope that you will be able to plug in the matrix form and the vector to solve a Schrodinger equation. Right? To solve for alpha beta is another business. We will do some simple thing. We are not going to solve in this class. That's not the purpose of this class, right? But you can use MATLAB or whatever to help you to solve this equation. Any questions? Okay. Now then I want to introduce one thing. Then it means that it's very important to find the matrix element. If you're given a problem, I want to find the matrix element. Because once I know the matrix element, I can solve the equation. If I don't know the matrix element, I have no way, right? So I want to interject something that we did not discuss much, is about how to find the matrix elements if you are given a matrix. So for any matrix M, I can write it as Mij. Someone tell me what is the meaning of this symbol? What is the meaning of Mij, by the way?
Row and column.
Thank you. It's the elements of M at row I and J column. Then, of course, I have all these elements, right? This is actually, in reality, this is M00, M01, M0, N-1, and then you repeat M10, M11, all the way to M1, N-1. And this Ij is exactly what you try to say. The element in row I and column J. That's it. So this one is actually does not give you any extra information, but say that now I denote the element as Mij. Yeah.
What does it say? MO.
This here?
After that.
Oh, M01.
After that.
Or M0 n minus 1. So because I have n by n matrix, right? So this is n minus 1. Sorry. Yeah, it's so difficult for this pen because this is an n by n matrix. Okay, just a label, right? Nij. So how do I find Ni? When I say how do I find Mij, it means how do I find the elements on the ith row and jth column, right? Now, so I'm going to just say that isn't that this m is just equal to summation I equal to 0 to 1 n minus 1 summation I j equal to 0 to n minus 1 and then I m I j j. Do you recall this? How do we find the eigenvalue of the, well, how do we compute the matrix from eigenvalue? At that time we say, okay, because this I and j is going to tell you which element you are going to put. And then Mij is just the location. I know this is not that clear for everyone. Let's do a quick practice. What is H? I claim that H equals to I equal to 0 to 1, J equal to 0 to 1, and then I, H, I, J, J, right? This is the two-dimensional case we're talking about, right? But is this correct? This basically saying what? You start with I equal 0, and then j equals 0. So what do you have? 0, h0, 0, 0. Plus 0, h01, 1. Plus 1, h10, 0. Plus 1, h11, 1. First of all, does this make sense to you from here to here? I just substitute 1 and 0 to Ij. Right? So I start with I equals 0, j equals 0, then these two are 0. I equals 0, j equals 1, then I have this, h01, like this, right? But these are numbers, correct? These are just numbers. And what is 0 in matrix form? 1, 0, right? What is 1 in matrix form? In vector form? 0, 1. So let's take an example. What is 1, h100? This is equal to 0, 1 times h10 times Thank you. How about others? What is this? Others, yeah. What is this? Row vector. And what should be the content? What is 0? 1, 0. It should be 1, 0, right? We have learned this before. So this equal to what? If you do the multiplication, you find that this is 0, 0, 1, 0 times h10. Do you see this? Do you agree with me? Basically, each of these ij tell you where to put this number in the matrix. And that's why each matrix can be represented in this way. Make sense? Okay, then let's continue. Got distracted. This is example, okay? This is just an example. Then let's continue with this one. Okay, so then M, isn't that is just equal to I times M times I, right? But what is I? Have you learned this completeness relationship in other class? So basically, if you take the basis of the system, you do the outer product, you add them together, it gives you I, identity. Okay, so this one you can refer to my book or Google if you want to learn how to prove it. But otherwise, you need to take this for granted, right? So I'm going to substitute this into it. Then this will become summation I. This is the first identity matrix. And then I add the J. Right? The other one is going to be summation J. Here it is. This I substitute with this one. This I substitute with this one. This is just the name, right? This is J, not I, right? This is just the name. So you arrange the terms. You will get summation I, summation J, I M, J, right? It is allowed to do that because summation multiplies summation, you can take them out, okay? This one you trust me. Then you have this I here, I M, J, right? J out, J cat J. This one. Okay? Now, but we just say that I call this 1, right? But from 1, isn't that these two are exactly the same, except that I have Mij and this one different, right? This is summation I, summation J, summation I, summation J. This is I cat J bra. This is I cat J bra. But these two are the same because both of them are M, right? So as a result, therefore, Mij equals to Imj. So if you want to find the elements of the matrix, you just need to find, but what are the Ij? Ij, of course, I need to emphasize again. It is the basis vector. For example, in this case, the Ij are the basis vectors 0 and 1. Okay? So in summary, how do I find the H00? It's going to be 0, H0. How do I find H01? Someone tell me. 0, H1. How about H10? 1, H0. How about H11? 1, H1. Thank you. Now, if you feel this is too much, it's fine. You don't need to know how to prove it. But having the knowledge about this completeness and also know understand what it is talking about is pretty important if you want to go to more advanced level in the future or feel comfortable in dealing with math. But the whole purpose of this slide is just to tell you that to find a matrix element, you just need to do this inner product. Use the cat of the first basis of the zero basis vector, multiply that by the Hamiltonian, and then take the bra of the first one, then you will get H00, right? H01 is the first one and the second one. That's it. And this one definitely you need to accept it and memorize it. If you want to know why, that is what I have proved to you. Any questions? A lot of math, right? But I don't require you to prove this, but you need to know this, the grid box. Okay, so then let's move forward. Let's talk about